Hello, folks. This lecture will highlight one of the fundamental reaction types that focus on trying to figure out where some pesky electrons go in some reactions. Hey! Okay. When electrons are transferred between atoms in a chemical process, the reaction is identified as an oxidation-reduction reaction or redox reaction. To identify these reactions, we need to be able to quantify the oxidation state or oxidation number. The oxidation state is the hypothetical charge we would give an atom in a molecule if all the bonding were ionic, with no covalent bonding character. Now, the oxidation state can either be positive, 0, or negative for the atom. Now, the total of the oxidation states for each atom in the compound must equal the total charge on the compound. Now, our job is easier if we're familiar with the common ions for the more common elements on the periodic table. The charges for the atomic species, which is based on proximity on the periodic table to the noble gas configuration, is usually also the given oxidation state for that atom when in compounds and molecules. Now, before we go on, I want to clarify the science a bit. We emphasize the word hypothetical when talking about oxidation states. We recognize that covalent bonds are not truly ionic. The actual charge differences of the atoms participating in the bonding of these covalent molecules are usually subtle and much smaller in magnitude than the oxidation states we attribute to them. But again, just like Lewis dots, oxidation numbers are a handy device in trying to understand what's going on in these reactions. Now, for an ionic compound with no polyatomic ions, the oxidation number for each atom is simply its charge. So for the ionic compound calcium chloride, CaCl2, we know that the preferred oxidation state or charge of the calcium atom is +2, and for each of the chloride atoms, their preferred oxidation state or charge will be -1. For calcium chloride, the total charge on the compound is supposed to be 0, and we see when we add up the oxidation numbers on each atom that they do indeed add up to 0. Now, if the substance is an element in its natural state, the oxidation number of the atoms will always be 0. So, for the sodium metal, the oxidation state of the sodium is 0, and if we're talking about the diatomic nitrogen gas, the oxidation state of each nitrogen atom is 0. Again, if the substance is covalently bonded, we treat each atom as if it were bonded ionically in the compound. Now, we'll do a few examples. For water, H2O, if things were ionic, each hydrogen would probably prefer a +1 charge, and the oxygen would want to have a -2 charge. These will be the oxidation states we will give for the atoms in the water molecule. Each hydrogen atom is assigned a +1 oxidation state, and each oxygen a -2 oxidation state. Furthermore, we know water is a neutral compound, and the oxidation numbers bear this out. The sum of the oxidation states of all the atoms equals 0. Now, a good rule of thumb is that in a covalent compound, hydrogen atoms will have an oxidation number of +1 most of the time, and oxygen atoms an oxidation state of -2 most of the time. Other main group elements that we can be sure about is the halides, which when bound to a single atom will have an oxidation state of -1. The oxidation state of most other main group elements can vary greatly. What we hope is that by knowing the total charge of the compound and the presence of the oxygen, hydrogen, halide atoms, and other elements of known ionic charge, we might figure out the oxidation state of the other atoms in the compound that we're not so sure about. So let's look at methane, CH4. We know the molecule is neutral, and we know that each hydrogen has an oxidation state of +1. So the carbon in this compound must have an oxidation state of -4. But in the compound carbon dioxide, CO2, which is also neutral, we know each oxygen atom has an oxidation state of -2. So in this molecule, carbon has an oxidation state of +4. This wild swing in possible oxidation states for carbon is one of the reasons carbon is such a fantastic atom to do chemistry with, and why this atom is so important in biological compounds in our bodies, such as DNA and RNA. Carbon can take a huge range of oxidation states, allowing it to easily bond with itself and with almost every other element on the periodic table. Now let's do one more example. Look at the polyatomic ion phosphate, PO4 3-. Here we see that the overall charge of this system is -3. Now we know that each oxygen atom has an oxidation state of -2, giving us a total of -8 in the 4 oxygen atoms. The phosphorus atom we can't be too sure about, but we know enough now to get a value. Since the overall charge must be -3 and the oxygen atoms have a total of -8 charge, the phosphorus must have an oxidation state of +5, making the sum of the phosphorus oxidation state and the 4 oxygen atoms equal to the overall charge on the phosphate ion, -3. Now, in a chemical reaction, if any of the oxidation states of atoms in the reactants change their oxidation state when they turn into products, then electrons must have been transferred, and we know that an oxidation reduction reaction has occurred. When an atom loses electrons, the atom is said to have been oxidized, and if an atom gains electrons, the atom is said to have been reduced. To keep this straight, I remember the word oil rig. The letters in the word stand for oxidation is a loss of electrons and reduction is a gain of electrons. Let's look at some examples of these kinds of reactions. First, we will look at a synthesis reaction between sodium metal and chlorine gas, which when combined makes sodium chloride solid. On the reactant side, everything is in its neutral elemental form, so the oxidation states of all the elements are 0. On the product side, we see we have an ionic compound so that the oxidation states will be the charges of the atoms. Sodium in the compound has an oxidation state of +1, and the chloride ion has an oxidation state of -1. The sodium atom lost an electron during the reaction process, going from an oxidation state of 0 in the reactants to +1 in the products. Sodium was oxidized in the reaction. The chlorine atom gained an electron, going from an oxidation state of 0 in the reactants to -1 in the products. Chlorine was reduced to chloride in this chemical process. This synthesis reaction is most definitely a redox reaction. Now let's look at the complete combustion reaction of methanol liquid at 25 degrees C as our second example. We know that for a complete combustion reaction of an organic molecule such as methanol, that the other reactant will be oxygen gas and the products will be carbon dioxide gas and liquid water. The balanced chemical reaction is shown. Now within the methanol molecule, the hydrogens have an oxidation state of +1 and the oxygen has an oxidation number of -2. So the carbon atom must have a -2 oxidation number to give us a neutral methanol molecule. The oxygen atoms in the elemental O2 gas will have a 0 oxidation state. Now we turn our attention to the products. The carbon dioxide and water molecule both contain oxygen, and the oxygen atoms are assumed to have a -2 oxidation state. The carbon atom in the carbon dioxide must have an oxidation number of +4 to balance out the oxygen atoms and give us a charge of 0 for that molecule. The hydrogen atoms have an oxidation state of +1 within the water molecule. Now looking at the carbon atom as we go from reactants to products, carbon has changed its oxidation state from -2 to +4, so it lost electrons, thus was oxidized in the chemical process. The oxygen atoms in the oxygen molecule had an oxidation number of 0 and must have been reduced to -2 since all the oxygen atoms in the products have a -2 oxidation state. There is no doubt that the combustion reaction is also a redox reaction. So it's a pretty safe bet that synthesis reactions from base elements and combustion reactions will always be redox reactions. The take-home message: look for oxidation state changes in the atoms as we transition from the reactants to the products in a chemical process. If they change, then we have a redox reaction. Redox reactions are such an important reaction class. The basic reactions of photosynthesis and other biochemical cycles rely on redox reactions to shuttle charge. Currently, redox combustion reactions are the source of the majority of the world's energy. But as we turn towards more renewable resources, we will rely on redox reactions to store energy in batteries. See, we aren't just learning chemistry here. We're learning about life. Makes you want to hug your computer right now, doesn't it? Anyway, hope to see you again soon. Bye.